So we're going to define a partial ordering, which is similar to equivalence relation, but kind of opposite because this one, partial ordering, is a relation that's reflexive, antisymmetric, and transitive. Okay, so it's kind of like the inverse of equivalence relation in terms of symmetry. Okay. So a set on which there's a partial ordering relation is called a partial order set or a poset. Okay. And when a relation is a partial ordering, we can represent the relation using a Haste diagram or Hast diagram or ordering diagram. We're going to look at those examples next. Okay. So first we're going to look at a few examples of partial ordering, like checking if it's a partial ordering or not. So let's say that look at the greater than or equal relation. Okay, so that relation is formed of pairs of points where the first one is greater than or equal to the second one on the set of integers, so positive or negative integers. Okay, so first we check to see if it's reflexive. Right, and it is because A is bigger than or equal to A, so all these are in my relation for all integers, positive or negative. Right, let's see if it's antisymmetric. Okay, so antisymmetric means that if A is not equal to B, then if A, B is in the relation, then B, A cannot be in the relation. Okay, and again, you can see that this is true because if A is bigger than or equal to B, then B cannot be bigger than or equal to A. So it's also antisymmetric. All right, now transitive. Okay, we're looking for, right, if AB is in R and BC is in R, then AC needs to be in R. Right? So if AB is in R, then that means A is bigger than or equal to B. If BC is in R, then B is greater than or equal to C. And by inequality properties, this would mean that A is bigger than or equal to C. So this is also transitive. Okay, so this is a partial ordering relation. Okay. Now let's look at the divisibility relation. So we visited this a couple of times. These are pairs of points such that A divides B. So the first number divides the second number. All right, so reflexive. Okay, so we need to show that AA is in that set, and it is because A divides into itself. Okay, we need to show that it's antisymmetric. Okay, so antisymmetric, if A is not equal to B, if AB is in the relation, then BA cannot be in the relation for all integers. Okay, so basically we need to show that if A divides B, then B does not divide A. And that's true. If a number divides another, then the bigger one is not going to divide the smaller one, so it's also antisymmetric. Okay, now transitive says that if A divides B and B divides C, then A is going to divide C. Okay, and this is true. I think we've proven it a couple of times, once earlier in this lesson and once a few sections ago. So this is also transitive. Okay, so the divides relation is a partial ordering on the set of integers. Okay, cool. All right, let's look at one more relation. So we're looking at actually these sets of points right here. The inclusion or the subset relation is a partial ordering on the power set of a set S. So our elements are pairs of sets. There are subsets of a power set. Okay, so this is the relation between those sets. Okay, so let's look at the reflexive property. So for this to be reflexive, then a set has to be a subset of itself, which it is. All right. Okay, let's look at the anti-symmetric property. Okay, so this is for sets A not equal to set B. If A is a subset of B, then B cannot be a subset of A. Okay, that's true. Right? If all the elements of A are in B and A has to be smaller than B, then B cannot be a subset of A. So it's anti-symmetric. And transitive, right? If A is a subset of B and B is a subset of A, then if A is a subset of B and B is a subset of A, then A has to be a subset of C. Okay? And this is also true. Kind of just like thinking of set properties, right? If A is a subset of B, then X is an element of B, and B is a subset of C, then that means that X is also going to be a subset of C. All right, so basically we start with this chain. X is an element of A, then X has to be an element of B, then X has to be an element of C. So basically, if X is an element of A, then X has to be an element of C. So this transitive property is also fulfilled. So this is a partial ordering. All right. Okay, so we're basically going to circle back to diagrams, directed graphs, and talk about a special kind of diagram or graph for relations called the Haste diagram. For a partial ordering, we can draw a simplified digraph that will kind of cut on the number of edges and also eliminate the arrows. Okay, so a Haste diagram takes the following into account. So because a partial ordering has a reflexive property, each vertex must be related to itself. So it must have a loop, and we don't draw the loops because they're assumed to be there. Okay, so Haste diagram, you eliminate the loops because you basically know that they're already there, so you don't need to draw them. Okay, so by the anti-symmetric property, connection between two distinct elements in the directed graph can only go one way, if at all. So where there is a connection, we agree to always place the second element above the first, and we just draw a connection without an arrow, just a line. Okay, so as long as the convention is to draw the second element above the first, then you don't need to draw the arrows. Okay. Now, by the transitive property, if there are edges connecting one element up to a second element and the second element to a third element, then there will be a direct connection from the first to the third. So we don't need to draw extra lines. As long as a line goes through three elements, we basically know that the first and the third element are automatically connected by the transitive property. Right, so that cuts down on the number of lines that we're using. So Haste diagrams are directed graphs where we can cut out all the loops, all the arrows, and extra lines because of it has the reflexive, the antisymmetric, and the transitive properties. And we can make a much simpler graph. And that's really useful when you basically have lots of elements. Okay, so let's look at some examples. Okay, so we're going to draw the Haste diagram representing the partial ordering A divides B. Okay, on the set 1, 2, 3, 4, 6, 8, 12. So we're going to draw these vertices. Before with the digraph, we said like the order doesn't really matter where you put them. But because we know that divides by is a partial ordering, we want to put elements in order. So kind of the lower ones will divide into the higher ones, and then the arrows will be understood. Okay, so we're going to have, let's say, 1 and 2 and 3. 1 divides into 2 and 3. And we're going to say, I'm going to put 4 here because like 2 divides into 4. We're going to put 8 here. So we go from lower to upper, and let's put 6 and 12. Okay, so this is a sort of good ordering right here. Let's draw the full digraph, and then we're going to show how it simplifies. Okay, so in the full digraph, because each number divides by itself, is going to have the self loops. So each of these are going to have loops. Okay, and now we're going to draw arrows from each of the numbers that divides into the other. So 1 divides into 2, 1 divides into 4, 1 divides into 8, 1 divides into 3, divides into 6, divides into 12. 2 divides into 4, 2 divides into 6, 2 divides into 8, 2 divides into 12. 4 divides into 8, 4 divides into 12. 3 divides into 6, 3 divides into 12, 6 divides into 12. Okay, so that's the full digraph, which even with this small amount of values, you can see that it gets pretty complicated. Okay, so let's simplify. So the reflexive property says that we can cut out all the loops. So let's drop the self loops. So we're going to redraw this without the loops. So let's have 1 and 2 and 4 and 8, 3 and 6 and 12. So those are my vertices. So without the loops, because we know this fulfills the reflexive properties, the loops are implied. So we have just the arrows. 1 goes to 2, 1 goes to 4, 1 goes to 8, 1 goes to 3, 1 goes to 6, 1 goes to 12, 2 goes to 4, 2 goes to 8, 2 goes to 6, 2 goes to 12, 3 goes to 6, 3 goes to 12, 6 goes to 12, 4 goes to 8. Okay, still lots of arrows. So now let's look at the transitive property. We'll do that one next. Okay, we don't have to go in order. So basically the transitive property says we can eliminate the edges. Okay, so basically we're going to combine edges, because if one line or arrow goes through 3 points, then we know that if it's going to go from the bottom one to the top one. Okay, so let's see what we mean. So let's draw our vertices again. 1, 2, 4, and 8, and 3 and 6 and 12 in here. All right, so basically what I mean is that we're going to just draw one arrow from 2 to 8, one line. We don't have to do double, because if it's passing through all these points, we know that 2 goes to 4 and also 2 goes to 8. Okay, all right, and we can sort of draw an arrow here, and 1 is going to go to 2, to 4, to 8. On this side, we're going to do this. All right, so 1 goes through all of this, 3 goes to 6 and 12, 6 goes to 12. Now we also need to cross over. We need to cross over here. But 2 going to 6 is also going to go to 12, okay? Because the sort of hit on that branch is going to go up, right? So that cut simplifies it even more, right? Now the anti-symmetric property gets rid of all the arrows, because as long as you go bottom through top, you're assuming that something on the bottom is going to point towards the top. So the anti-symmetric property is going to simplify it even more. Let's look at purple. We're going to have our vertices 1, 2, 4, and 8, and 3, and 6, and 12. Okay, so our most simplified diagram is going to look like this. Oh, I think I'm missing one. Sorry for the green. I missed this one. There has to be a crossover there too. All right, so the pink purpley one is the Haste diagram. So this is the Haste diagram of the divide, A divides by B. So if there's sort of agreement on some conventions, like smaller numbers on the bottom and higher ones to the top, then you can drop the loops, you can drop the arrows and merge some lines together, and you get the relationship between these values in the relation in a much simpler format. So again, these are used for partial orderings because of their reflexive, their anti-symmetric, and their transitive. All right, so when you draw a Haste diagram, you don't have to go through all this process. I'm showing it just to show how sort of all the complication drops out to get to the simplistic one. You would try to basically draw a Haste diagram straight away to here. So for example, let's look at the Haste diagram representing the partial ordering. Each pair of points are sets, where A is a subset of B on the power set of S, which is A, B, C. Okay, so let's write the power set to kind of see how things are connected. So I have the null set, I have all the single ones, and I have the double ones, AB and AC and BC, and then I have ABC. Okay, so we're going to put our vertices with sort of the simplest one at the bottom, and then the single ones. Let's have A and B and C. Oops, there you go. And then the double ones a bit higher up. Let's put A, B here, AC here, and BC here. And we're going to put ABC on top. All right, so let's draw. All right, so no loops, although each set is a subset of itself. The loops are implied. Okay, so we're going to go from the null set to the ones that are sort of in front of it, the first level ones. Okay, now A is a subset of AB, and A is a subset of AC. B is a subset of AB, and B is a subset of BC. C is a subset of AC, and C is a subset of BC. Okay? All right, but the null set, it kind of follows the lines. The null set is also a subset of AB. And the null set is also a subset of AB through here. And the null set is also a subset of BC. Okay. All right, so let's see now. AB is a subset of ABC, and AC is a subset of ABC, and BC is a subset of ABC. But I don't need to draw the lines from A to AB, and B to ABC, and C to ABC, because you can follow the diagram to get you there. So for example, A is a subset of ABC because you can get there by following this line and that line, or this line and that line. Okay? And C is a subset of ABC because you can follow this line to that line, or this line to that line. Okay, so as long as you can get there through a path, then the Haste diagram, you don't have to draw a separate line from this node to that node. Okay? And again, arrows are not necessary because the order follows from the bottom to the top. Okay, so this is an example of a Haste diagram for this partial ordering of A being a subset of another in the power set of a set. Okay, so this ends this section right here.